February 14, 1943. WWII, Tunisia. A single American M4A1 Sherman tank, captured intact and operational, sat motionless in the blistering desert sun. Its steel hull, once adorned with the proud star of the U.S. Army, now bore a hastily painted German cross, an ironic trophy for Panzer Battalion 501. The officers surrounding it scribbled notes, their expressions a mixture of curiosity and unease. They had expected a marvel of brute force or intricate engineering. What they found instead was something far more insidious, a machine that simply worked. No ingredients, no jam transmissions, no broken final drives. Every kilometer the tank traversed shattered assumptions about what German engineering considered possible. This was War Daddy 2, serial number USA 306-7641, built by Limer Locomotive Works and assigned to Company G, 1st Armored Regiment, 1st Armored Division. In the hands of German reconnaissance teams, it endured 350 kilometers of harsh North African terrain in 4.5 days without faltering, a feat that would trigger panic among Wehrmacht engineers and reshape their understanding of armored warfare. Imagine discovering that your most advanced, meticulously engineered tanks, Panthers and Tigers, would break down under the conditions this single Sherman conquered effortlessly. Every gear, every drive, every engine component whispered a truth Germany had ignored. Industrial reliability mattered more than raw specifications. If you want to understand how this one captured Sherman forced German engineers to admit their own failures and why it reshaped tank design for decades, stay with me until the very end, because the lessons of War Daddy 2 are not just history. They are the blueprint for industrial and operational supremacy in warfare. Mid-February 1943, WWII, Tunisia. The North African desert stretched endlessly under a pale winter sun, its sand shifting like liquid gold across jagged ridges. Among the scattered remains of the battlefield, a singular object drew the attention of Panzer Battalion 501, a Sherman M4A1 tank, captured intact after fierce skirmishes with the American 1st Armored Division. The machine, nicknamed War Daddy 2 by its original crew, sat quietly, its American star almost entirely obscured by the crude German cross hastily painted over the hull. The officers surrounding the vehicle scribbled furiously in leather-bound notebooks, their faces betraying both fascination and disbelief. Captain Hans Richter, a seasoned tank commander, bent over the glassy plate, running his fingers along the armor and muttering in disbelief. "It's functional," he murmured. "Every component works." Unlike the Panthers and Tigers under his command, this enemy machine showed no signs of overheating, no strained final drives, no jammed transmissions. The Germans had expected a marvel of theoretical engineering, but instead found industrial reliability perfected. The Sherman's Continental R975 radial engine gleamed beneath the engine cover, its maintenance marks meticulous, yet simple enough that a trained mechanic could maintain it without specialized tools. The herringbone-cut gears in the transmission caught immediate attention from Lieutenant Klausberg, who had spent months struggling with the finicky gears of the Panther D. Such durability, he noted, without the need for constant adjustments, unheard of. Across the battlefield, the desert sun revealed a truth that German engineers had long avoided. America had mastered mass production at a scale and consistency Germany could not match. Upon reaching Sfax, the tank was carefully loaded onto a cargo ship bound for Germany. The Army Weapons Office issued explicit orders. The Sherman must arrive intact and operational. German intelligence had received fragmentary reports about American tank production, but no statistics could compare to witnessing a real, functioning vehicle. War Daddy 2 represented American industrial philosophy, a blend of pragmatic engineering and mass production excellence, designed for sustained operation in combat. It was a revelation the Germans could neither ignore nor replicate. On board the ship, engineers began preparing for its eventual examination at the Kummersdorf Proving Grounds. The tank's presence posed not only a technical challenge, but also a philosophical one. How could a relatively lightly armored tank, built with straightforward manufacturing techniques, outperform vehicles painstakingly engineered for battlefield supremacy? The answer would come not from its gun or armor, but from a concept the Germans had overlooked entirely: reliability at scale. Even as the Mediterranean waves carried War Daddy II northward, German officers and engineers debated its implications. Major Friedrich Speer, liaison for the Wehrmacht's armored division, wrote in his journal, "This tank operates without interruption, without the constant need for expert attention. If our industry could produce such machines, our entire approach to armored warfare would be transformed." Yet for every observation, every note, a quiet fear began to grow. Germany could not match this industrial might, and no amount of technical knowledge would bridge the gap. When the cargo ship docked in Hamburg, War Daddy II was immediately transferred to a transport rail car for the journey to Kummersdorf, south of Berlin. Soldiers from the Panzer Reconnaissance Unit escorted the tank, guarding it against potential sabotage. Along the way, it became apparent that this was more than just a captured tank. It was a mirror reflecting Germany's own industrial deficiencies. Each mechanical system performed flawlessly. The transmission with its 5 forward speeds, synchronized from 2nd through 5th gear. The Continental R975 engine, maintaining optimal performance in extreme temperatures. And the final drives, engineered with herringbone gears that distributed stress evenly across the teeth. Every component challenged German assumptions that technical sophistication alone could guarantee battlefield supremacy. By the time War Daddy II arrived at Kummersdorf, the initial inspection had begun. Engineers from multiple branches, mechanical, automotive, and weapons, photographed every angle, measured armor thickness with precision instruments, and documented construction techniques that seemed almost too simple. Where German designs demanded highly trained specialists to maintain, the Sherman could be serviced by a mechanic with basic automotive experience. A revolutionary idea to German observers. Lieutenant Berg, assigned to evaluate powertrains, noted that even the desert test course would not fully stress the Sherman's mechanical endurance. Every mile and obstacle in Tunisia had already demonstrated a capability beyond what German tanks could achieve even under ideal conditions. That evening, as War Daddy II rested under tarps in the proving grounds, Major Speer reflected on the day's observations. "We have knowledge. We understand its superiority. Yet knowing does not equate to producing. The gap is vast, perhaps unbridgeable." In that moment, the Germans realized that their technical expertise, honed over decades, was being tested not by brute force, but by practical, reliable design born from industrial experience. And so, the stage was set. War Daddy II would undergo months of exhaustive testing, revealing not only the strengths of American tank engineering, but also the profound weaknesses in German industrial philosophy. Its journey from Tunisia to Germany was more than a logistical feat. It was the first step in a revelation that would resonate through the remainder of the war, quietly rewriting the rules of armored warfare without firing a single shot. March 5, 1943, Kummersdorf Proving Ground, Brandenburg, Germany. The snow-covered landscape stretched across 25 kilometers south of Berlin, a stark contrast to the scorching deserts of Tunisia, where War Daddy II had first demonstrated its resilience. The Sherman M4A1, still bearing its name on the hull, rolled off the transport rail car with an almost silent confidence. German engineers, dressed in heavy winter coats and fur-lined hats, circled the vehicle, clipboards and calipers in hand, prepared to dissect every aspect of the American tank. The proving ground had been established to test both German and captured enemy vehicles under controlled conditions, a crucible where assumptions met reality. Teams of specialists were already busy. Mechanical engineers checked engine tolerances, automotive experts measured suspension travel, and weapons officers examined turret traverse mechanisms. Every inch of the Sherman was scrutinized. Unlike German tanks, which required painstaking alignment and careful handling, the Sherman's components were straightforward, modular, and standardized. Lieutenant Klausberg, assigned to powertrain evaluation, noted immediately the sophistication, yet simplicity, of the transmission. Herringbone-cut gears, long dismissed as impractical for mass production, handled loads effortlessly. In contrast, the Panther's straight-cut transmission demanded exact tolerances and constant maintenance. Berg ran the Sherman through an initial obstacle course designed to replicate battlefield conditions: uneven terrain, shallow trenches, sandy gravel, and artificial mud patches. Every hill climb, every pivot turn revealed operational ease that German tanks could only dream of. The Panther struggled on the inclines, the final drives whining under stress, while the Sherman's powertrain remained nearly silent, its gears meshing smoothly as if mocking German assumptions. Meanwhile, Captain Hans Richter observed the engine's performance. The Continental R975 radial engine maintained steady RPMs across all loads, with no overheating despite the repeated acceleration and deceleration. German reports had predicted desert-level stress would cause engine failure within a few hundred kilometers, yet WWII had already proven otherwise. Engineers noted the air filtration system's efficiency. Fine desert sand, notorious for crippling German vehicles in Tunisia, passed through unimpeded. Every system functioned without specialized attention, a stark contrast to the meticulous daily maintenance Panther crews required even under ideal conditions. By mid-March, the Sherman underwent systematic mechanical dissections. The transmission was removed and measured, where patterns were minimal, far below what would be expected after extensive field use. The final drives, built with the same herringbone principles, resisted the crushing torque that had destroyed Panther and Tiger units repeatedly on the Eastern Front. Observers documented the ingenious yet simple synchronization mechanism that eliminated the need for double clutching, a procedure every German tank driver had learned by painful repetition. Ordinary soldiers could now operate the tank effectively with minimal training, a radical departure from German doctrine, which assumed highly trained specialists were always available. Simultaneously, engineers examined fuel consumption and operational endurance. WWII could traverse over 2,000 kilometers with standard maintenance, 4 times the range of early-model Panthers before requiring major servicing. Lieutenant Berg noted in his journal, "The disparity is not marginal, it is fundamental. The Sherman is designed to function continuously. German tanks are designed to impress on paper. Every system, from the simple but effective cooling system to the modular electrical components, reflected a philosophy prioritizing operational longevity over theoretical superiority. Weapons specialists, led by Oberleutnant Fritz Schumann, inspected the Sherman's armament. The 75mm M3 gun, stabilized by early Euro mechanisms, allowed more accurate fire while on the move than many German tanks could achieve under static conditions. Schumann compared it to the Panther's 75mm KWK-42, noting that although the Panther had superior penetration, it required ideal positioning, precise calculation, and near-perfect maintenance just to function reliably. The Sherman, by contrast, could deliver competent firepower consistently, even when conditions were far from ideal, a practical advantage the German officers were slow to acknowledge. By late March, Kummersdorf engineers organized a side-by-side comparison. WWII sat beside a freshly built Panther SF Diam and a Ferdinand tank destroyer. Observers, including Major Friedrich Speer, witnessed initial mobility trials. The Sherman ascended a 30-degree slope with ease, transmission smooth, engine steady, and driver confident. The Panther struggled to maintain traction, its final drives groaning under torque, while the Ferdinand, despite its formidable 65-ton mass and electric transmission, stalled halfway. Recovery crews were required to pull the Ferdinand to the top, highlighting the practical failures German tanks faced in real conditions. Every observation was meticulously documented. Engineers measured wear, analyzed mechanical stress, and calculated operational readiness. What emerged was undeniable. German designs, though technically impressive, suffered from reliability shortcomings that American mass production philosophy had already overcome. Panther battalions, even at full strength, reported operational readiness rates as low as 16% during field operations, primarily due to mechanical failures. The Sherman, even after extended use, remained operationally superior. By the end of March 1943, the psychological impact on German engineers was profound. Captain Richter reflected in his notebook, "We are confronted not merely with an enemy tank, but with a revelation about our own industrial inadequacies. We have the knowledge, we know the problem, yet we lack the means to replicate it." War Daddy 2 had become more than a vehicle. It was a mirror. Every turn of its gears, every mile it traversed, every hill it climbed without failure reflected a fundamental miscalculation in German armored philosophy. Precision engineering had been prioritized over practical reliability, and mass production principles had been ignored in favor of technical showmanship. By the conclusion of Part 2, German engineers faced an unsettling truth. American tanks were not superior due to firepower or armor alone. They were superior because they worked consistently, under any conditions, for any crew, without the constant hand-holding German tanks demanded. The stage was now set for further testing that would examine the Sherman's endurance, field reliability, and adaptability, exposing the depth of German industrial limitations and challenging every assumption the Wehrmacht held about armored warfare. June 6 to 7, 1943, Hillis-Leen Artillery Range, Brandenburg, Germany. The first rays of the morning sun glinted off the snow-melted mud of the proving grounds. War Daddy 2, the captured M4A1 Sherman, sat alongside Germany's latest armored marvels, the Panther SF Diam and the Ferdinand tank destroyer. This was more than a demonstration. It was a crucible designed to compare theoretical power with practical reliability, to reveal whether German technical sophistication could withstand real-world stress against an enemy designed for continuous operation. Major Friedrich Speer, liaison between the Armaments Ministry and the Wehrmacht, observed keenly. The artillery range buzzed with activity as engineers, mechanics, and officers meticulously documented every variable. The Sherman's Continental R975 radial engine purred steadily as it approached the first incline. Lieutenant Klausberg, assigned to powertrain analysis, held his stopwatch, recording RPM consistency, engine temperature, and gear synchronization under load. War Daddy 2 climbed the 30-degree slope effortlessly, transmission smooth, power delivery constant. The Panther followed, struggling to maintain traction despite its more powerful 700-horsepower Maybach HL230 engine. The Ferdinand, massive at 65 tons, stalled halfway up, forcing recovery crews into a laborious extraction process that lasted over an hour. The contrast was stark. German tanks, painstakingly engineered and expensive, faltered under basic operational demands. By comparison, the Sherman's 5-speed, synchronized manual transmission eliminated the need for double clutching. Ordinary soldiers could operate it efficiently, requiring minimal specialized training, something Panther crews could only dream of. Captain Hans Richter noted in his journal, "This tank does not demand perfection from its driver. It compensates for human error while performing reliably under stress. This is not a weakness. It is industrial genius." Weapons officers, led by Oberleutnant Fritz Schumann, tested the Sherman's 75mm M3 gun across varied terrains. Early Euro stabilization allowed accurate fire on the move, a capability largely absent in German tanks that relied on static firing positions. While the Panther's KWK 42 gun possessed superior armor penetration, its effectiveness was frequently compromised by mechanical limitations and the need for precise positioning. The Sherman, in contrast, could deliver practical firepower consistently, regardless of terrain or driver skill. Extended trials over the following weeks examined suspension and track endurance, engine cooling, and electrical system reliability. War Daddy 2 traversed hundreds of kilometers through simulated battlefield conditions, from muddy tracks to rocky inclines. The results confounded German observers. No overheating, no transmission failure, no broken final drives. The herringbone gears in both transmission and final drives absorbed stress far more effectively than the straight-cut systems used in Panthers, whose failure rates were alarmingly high under even moderate strain. Operational endurance trials further highlighted the disparity. WWII maintained functionality for over 2,000 kilometers without major maintenance, a distance 4 times that of early model Panthers. German reports indicated Panther operational readiness averaged below 40% throughout 1943, with some units reporting catastrophic failures, leaving fewer than 1 in 5 tanks combat-ready. By comparison, the Sherman's field reliability provided a decisive advantage. Tactical mobility and sustained combat operations without continuous mechanical attention. The logistical implications became increasingly apparent. German tank doctrine had long assumed highly trained specialists would always be available for maintenance. Sherman design philosophy assumed exactly the opposite. Ordinary mechanics with civilian automotive experience could maintain and repair the vehicle using basic tools. Components were modular, standardized, and interchangeable across multiple manufacturers, Caterpillar, Buick, and Ford, ensuring consistent quality and rapid field repair capability. By contrast, Panther and Tiger production suffered from subtle variations between factories, creating compatibility issues and increasing downtime. By late June, internal reports circulated through the Wehrmacht and Armaments Ministry. Engineers documented operational range, powertrain efficiency, and transmission behavior in exhaustive detail. They measured synchronized gears, final drive reliability, and engine lifespan. The findings were unambiguous. American tanks had mastered operational reliability, Germany had not. WWII, a single captured vehicle, exposed systemic flaws in German armored doctrine, production, and logistics. Even German field units acknowledged the disparity. Panzer divisions operating on the Eastern Front and in Italy sent captured Shermans into service with minimal modification. Unlike Soviet T-34s, which required extensive adjustments, the Sherman operated as designed. Reports highlighted improved tactical effectiveness, reduced mechanical downtime, and increased confidence among crews. For the first time, German commanders recognized that operational reliability, not armor thickness or firepower, determined battlefield effectiveness. The psychological impact on German engineers was profound. Major Speer reflected, "We have measured, we have documented, we understand. Yet, knowing this does not grant us the capacity to replicate it." Their industrial system, honed through decades of civilian automotive experience, surpasses our technical knowledge in practical execution. By the end of summer 1943, extended trials at Kümmelsdorf had transformed WWII from a captured tank into a benchmark for industrial excellence and mechanical reliability. Every test, every mile, every component verified the lesson that Germany could not achieve sustained operational superiority through technical specifications alone. The Sherman had revealed a stark truth. Reliability, maintainability, and industrial scale mattered more than theoretical perfection. September 12, 1943, Kümmelsdorf Proving Ground, Brandenburg, Germany. The autumn chill settled across the proving grounds, but the atmosphere inside the workshop was tense with anticipation. Following months of exhaustive testing of the captured M4A1 Sherman, additional vehicles had arrived, including M4A2 diesel variants, M4A3 gasoline models, and British-modified Firefly Shermans, equipped with the formidable 17-pounder anti-tank gun. Each new arrival offered fresh data, challenging assumptions about American tank design and industrial methodology. The M4A2, powered by twin General Motors 6046 diesel engines, was first on the assessment list. Lieutenant Klausberg and his team subjected the vehicle to the standard Kümmelsdorf endurance course, cross-country maneuvers, mud pits, rock fields, and steep inclines. Observers were immediately impressed by the diesel engine's efficiency. Fuel consumption was significantly lower than the gasoline-powered M4A1, while delivering comparable power. In contrast, German diesel experiments had consistently failed to produce reliable engines for armored vehicles. Attempts to adopt complex fuel injection systems and precise manufacturing tolerances proved unmanageable under wartime conditions. The American solution was elegantly simple. Diesel Shermans performed flawlessly while maintaining mass production efficiency. The M4A3, powered by the Ford JA V8 gasoline engine, followed. Its performance exceeded expectations, with remarkable acceleration, power-to-weight ratio, and operational endurance. German engineers, accustomed to frequent breakdowns in Panther and Tiger units, documented engine behavior under extreme load and temperature variations. Every test confirmed what the M4A1 had demonstrated. American tanks were built with margins of safety and operational flexibility that German vehicles lacked. The British Firefly Sherman presented the most intriguing case. By replacing the standard 75mm gun with a 17-pounder, British engineers had addressed the Sherman's relative weakness in firepower. The Germans scrutinized turret modifications, noting how minimal adjustments had been needed to accommodate the larger weapon due to the Sherman's generous turret ring. Panther tanks, despite their technically superior armament, had no capacity for such straightforward upgrades. Observers remarked that the Firefly exemplified one of the key strengths of American design philosophy: built-in adaptability. A vehicle could be enhanced to meet evolving battlefield demands without requiring complete redesign. By mid-October, systematic testing focused on reliability under simulated combat conditions. Tanks were driven for hundreds of kilometers without maintenance, then disassembled for inspection. Results were consistent across variants: minimal wear on transmissions and final drives, robust suspension components, engines tolerating extreme temperatures, and components remaining fully operational after repeated stress. Field modifications, like sand filters for desert conditions or extra armor for Normandy, were integrated seamlessly, demonstrating the flexibility of the original Sherman design. In parallel, German engineers continued comparative testing against domestic tanks. The Panther's straight-cut transmissions failed repeatedly under stress, often requiring field replacement or complete disassembly. Final drives, inherited from Tiger designs, were prone to catastrophic failure within a few hundred kilometers. The Sherman's herringbone gears in both transmission and final drives endured continuous operation without intervention. Panther crews on the Eastern Front reported operational readiness as low as 16% during 1943, while Sherman units maintained functional strength above 80% even under harsh conditions. Operational endurance trials highlighted an additional advantage: maintenance simplicity. Whereas German tanks demanded constant expert attention and complex tools, Sherman components were modular and interchangeable. Caterpillar, Buick, and Ford all produced identical parts, allowing field mechanics to swap components without adjustments. Observers noted that even complex engines like the Chrysler 57 multibank 30-cylinder could be troubleshooted with relative ease compared to Maybach engines, whose maintenance required specialized expertise. By late October, the psychological impact on German engineers was undeniable. Major Speer recorded in his journal, "The Sherman is not merely a tank, it is an industrial statement. Reliability, simplicity, adaptability. These are principles our designs lack. They produce vehicles that look impressive but fail consistently under operational conditions." Reports circulated detailing the comparative advantages: synchronized transmissions eliminating double clutching, engines resilient across temperature extremes, standardized components enabling rapid field repair, and adaptability for upgrades like the 17-pounder Firefly conversion. The Firefly variant particularly alarmed weapons specialists. Its turret modifications required minimal labor, yet allowed the Sherman to defeat heavier German armor at long range. By contrast, the Panther could not accommodate significant upgrades without complete redesign, highlighting a critical limitation in German armor doctrine. German commanders realized that operational effectiveness depended not just on armor thickness or gun caliber, but on vehicles reaching the battlefield ready to fight. By the end of autumn 1943, Kumersdorf had compiled an exhaustive database of Sherman performance across multiple variants. Observations were clear. American industrial maturity and practical design principles had produced tanks that were not only reliable, but capable of continuous adaptation to battlefield requirements. German tanks, despite superior specifications on paper, could not match this performance. Engineers recognized that reliability, ease of maintenance, and operational endurance were decisive factors in modern mechanized warfare, factors German design philosophy had consistently undervalued. The lessons of 1943 extended beyond the mechanical. Field reports confirmed what the Kummersdorf trials revealed. Sherman tanks, whether M4A1, M4A2, M4A3, or Firefly, delivered sustained combat power, allowing units to operate continuously without the logistical burdens that crippled German armored divisions. Panther and Tiger battalions, despite technological sophistication, were frequently immobilized by mechanical failures. The Sherman's combination of reliability, maintainability, and adaptability offered a tactical advantage that German engineers could not overcome with technical knowledge alone. As the year drew to a close, German officers and engineers quietly acknowledged the reality. American tank design philosophy, grounded in decades of automotive industrial experience, had achieved what German precision engineering could not: vehicles that simply worked day after day in the harshest conditions, without the constant hand-holding German tanks required. December 1st, 1943, Eastern Front, near Kursk, Soviet Union. German panzer divisions huddled in freezing mud, preparing for the upcoming Operation Citadel. Mechanical failures plagued the units more than Soviet opposition. Panthers were immobilized by final drive breakdowns. Maybach engines overheated after short marches, and transmissions seized under the slightest misalignment. In contrast, captured Sherman tanks, both M4A2 diesel and M4A3 gasoline models, performed admirably in German hands. Units assigned these vehicles reported that they required minimal maintenance, could traverse rough terrain without stoppages, and reliably delivered firepower in combat. General Wolfgang Tommel, Chief of Staff to the Inspector General of Panzer Troops, reviewed reports from the 26th Panzer Division. Operational readiness for Panther tanks averaged only 16% during July 1943 at Kursk, with catastrophic breakdowns outpacing enemy action. By December, some units reported readiness climbing to just 37%. Sherman-equipped companies maintained operational strength above 80%, demonstrating the practical significance of industrial reliability in warfare. German commanders began to understand that field functionality, not specifications, determined combat effectiveness. January 1944 brought further evidence of Sherman superiority. Captured vehicles were pressed into reconnaissance and mobile reserve roles, where consistent mechanical reliability was essential. Units relying on German tanks were forced to restrict movements to conserve component life. Every kilometer risked immobilization. Sherman-equipped crews, by contrast, could operate continuously, completing multiple missions without returning for maintenance. Lieutenant Klausberg noted in his journal, "The Sherman demonstrates operational foresight built into its design. German tanks require constant monitoring. The Sherman requires none." Industrial capacity increasingly influenced these outcomes. Allied bombing campaigns targeted key German tank production facilities, devastating supply chains. The Maybach engine plant in Friedrichshafen suffered severe damage on the night of April 27 to 28, 1944, with 322 Royal Air Force bombers inflicting catastrophic losses. Adjacent ZF gearbox factories were similarly crippled, halting transmission production for 6 months. Replacement parts became scarce, and production quality declined sharply. Field reports documented an uptick in Panther and Tiger mechanical failures, exacerbating already low operational readiness. Simultaneously, German reliance on forced labor introduced additional risks. Sabotage, either intentional or through improper assembly, created mechanical faults in engines, transmissions, and final drives. In contrast, Sherman production, conducted in safe American factories, remained uninterrupted. Skilled laborers operated under stable conditions with access to quality materials, consistent standards, and proper oversight. Tanks left the factory fully operational, reflecting decades of automotive experience applied to military production. By February 1944, German engineers compiled comprehensive comparative data. Engine lifespans for diesel Shermans exceeded 3,000 kilometers under normal maintenance, while Panther engines barely reached 1,000 kilometers, even after improvements. Transmission efficiency for Shermans was markedly superior, with synchronized gears minimizing driver error. Final drives on captured Shermans rarely failed, while German counterparts broke down under minimal stress. Field deployment confirmed these findings. Operational availability, not theoretical firepower or armor, determined battlefield utility. Reports from German units operating captured Shermans reinforced the Kumersdorf data. Crews consistently praised the tank's reliability, noting that focus could remain on tactics and combat effectiveness, rather than constant maintenance. Letters from the 10th SS Panzer Division, which had captured 12 M4A3 Shermans in January 1945 at Hellesheim, detailed how the vehicles required minimal adjustments and could sustain prolonged operations. Panther and Tiger units, by contrast, were immobilized repeatedly, reducing combat effectiveness and morale. Industrial disparity became painfully obvious in late winter 1944. Sherman mass production continued at unprecedented rates, over 49,000 tanks produced during the war, exceeding total German tank production of all types combined. Lend-Lease shipments supplied British and Soviet allies, reinforcing frontline capabilities. German forces, constrained by bombing, resource shortages, and industrial sabotage, could not match these outputs despite advanced technical knowledge. Knowledge without production capacity was meaningless. The Sherman exemplified the lethal combination of engineering competence and industrial power. By March 1944, German engineers had to confront an unavoidable truth. Operational failures were systemic, not anecdotal. Field reports documented Panther readiness at 37%, Tiger units similarly constrained, while Shermans maintained reliability across multiple theaters. Even incremental improvements in German production, better engines, reinforced final drives, did not approach the baseline reliability inherent in American designs. Industrial philosophy had determined the war's armored outcome. A tank that functioned consistently in combat was infinitely more valuable than a technically superior but mechanically fragile machine. In summary, the late 1943 to early 1944 period crystallized lessons from Kumersdorf and field deployment. German reliance on precision engineering without industrial redundancy, combined with logistical constraints, produced tanks that were impressive on paper but unreliable in practice. Sherman design, derived from decades of automotive experience, prioritized operational durability, maintainability, and adaptability, ensuring that vehicles delivered consistent combat performance regardless of conditions. The industrial advantage had become a decisive tactical and strategic factor. June 6, 1944, Normandy, France. Allied forces stormed the beaches under relentless fire, armored units advancing inland to support infantry breakthroughs. Sherman tanks, primarily M4A3 variants with 4 GAA engines, proved indispensable. Across hedgerows, through the Bocage country, mechanical reliability determined operational effectiveness. Where German Panthers and Tigers frequently stalled or broke down, Shermans delivered sustained support. Units could push forward continuously, supply lines maintained, artillery coordination effective, and infantry supported by fully operational armor. Reports from the 1st Armored Division highlighted the stark contrast. Shermans endured over 150 kilometers of rugged movement, climbing steep embankments and fording streams without major maintenance. Engine temperatures remained stable, transmissions shifted smoothly, and final drives endured the stress of uneven terrain. Captured German engineers observing these operations noted, with growing alarm, that mechanical reliability had become the Sherman's deadliest advantage. Even advanced German designs, optimized for firepower and armor, faltered under conditions that the Sherman handled routinely. By December 1944, during the Ardennes offensive, German planners attempted to use captured Shermans for infiltration. The 150th Panzer Brigade received 2 operational Shermans. Only one functioned reliably, demonstrating how critical operational readiness was in high-stakes maneuvers. German tanks, no matter how technically advanced, could not sustain similar operational tempos. Major Friedrich Speer's notes from this period reflected a grim realization. Our tanks are a marvel of engineering, yet they fail at the simplest of tasks. The Sherman's reliability is more formidable than our heaviest armor. Early 1945 brought further confirmation. The Panzer Commission documented catastrophic final drive failures across all German tank types. Before the Eastern Offensive, over 500 defective final drives in Panzer IVs, 370 in Panthers, and roughly 100 in Tigers were reported. Additional failures in Hetzer tank destroyers added to the tally. General Wolfgang Tommel emphasized operational consequences. Without reliable tanks, missions could not be executed and confidence in vehicles eroded. Entire units abandoned functional equipment to avoid being stranded by mechanical failure, a scenario virtually impossible with Shermans. German attempts to press captured Shermans into combat highlighted the practical advantages American engineering provided. Even in desperate defensive operations near Berlin, Sherman tanks performed consistently until destroyed by enemy fire or fuel exhaustion. Their ability to function reliably under continuous operational stress contrasted sharply with German vehicles, which failed frequently due to mechanical limitations exacerbated by wartime shortages, Allied bombing, and overextended logistics. Allied intelligence, reviewing post-war documentation, corroborated the findings from Kummersdorf. Systematic examination of destroyed German tanks revealed that mechanical failure caused as many losses as combat damage. Broken final drives, seized transmissions, and burned-out engines were rampant. The Sherman's design philosophy, robust powertrains, synchronized transmissions, and field-serviceable components, had solved problems German engineers had never fully addressed: maintainability and sustained operational readiness under combat conditions. By spring 1945, German engineering offices acknowledged what months of field reports, Kummersdorf testing, and captured vehicle analysis had repeatedly proven: operational reliability was paramount. The Panther and Tiger, despite technical sophistication and impressive specifications, could not be counted on to reach the battlefield fully functional. The Sherman, in contrast, consistently arrived ready for combat. This advantage shaped tactical possibilities, allowing Allied armored units to maintain offensive pressure while German units were forced to conserve their remaining operational vehicles. The Sherman's legacy extended beyond wartime operations. Post-war analysis influenced the development of the Leopard 1 main battle tank in West Germany. Designers consciously prioritized reliability, maintainability, and modular components, drawing directly on lessons learned from American automotive and tank engineering. Features such as robust powertrains with substantial safety margins, simplified maintenance requiring minimal specialized tools, and standardized components enabling rapid field repair mirrored the design philosophy that had made the Sherman operationally superior. As German forces collapsed and Berlin fell, War Daddy II and other captured Shermans symbolized more than technical intelligence. They were tangible evidence of industrial maturity and practical engineering applied to warfare. One tank, with its serial number and name painted on the hull, encapsulated the decisive lesson of the entire conflict. Functionality beats theoretical superiority, and reliability determines victory. If you've made it this far, you've just glimpsed the hidden story behind one of World War II's most decisive weapons. Imagine witnessing the moment German engineers realized that their most feared tanks were no match for the practicality of American design. Now, I challenge you. Share this story with someone who thinks victory is about size or firepower alone. Hit that like button, subscribe for deeper dives into armored warfare history, and comment below. Which aspect of a Sherman's design do you think was the most game-changing? Your thoughts could inspire the next deep historical analysis. By May 1945, the reality was undeniable. The Sherman did not win the war through superior armor or firepower alone. It won through industrial capability, operational reliability, and maintainable design, factors that Germany could never replicate under the pressures of multi-front warfare. Every mile driven without breakdown, every mission completed without mechanical intervention, and every field repair conducted with basic tools demonstrated the practical supremacy of American engineering. War Daddy 2, and the thousands of Shermans it represented, had shown the world that a reliable machine in capable hands could outperform technically superior designs crippled by their own complexity. The Allied victory, as much as any strategy or battlefield maneuver, was cemented by industrial foresight and engineering pragmatism, principles that continue to inform military vehicle design to this day.